Right, so the first thing I'm going to talk about is composition and chemistry, because those really are the fundamental things that set things like radiation. But what I decided to do was also have something of an anti-lecture on things we don't know. But I'm using that as a foil to explain things we do know. But essentially, as I look at it, scientific progress is about explaining the unfamiliar with the familiar. And so we need to identify the unfamiliar to see the useful problems to address in the future. I'd also say that knowing a subject's history is important. Old ideas, once dismissed, occasionally return to be the actual answer. Or, as we were discussing earlier, it's useful to know what people thought about when they were looking at solar system objects remotely in an exoplanet context. And although Isaac Asimov once said that the solar system is 4 planets plus debris, and I live on a piece of the debris, my focus is things that I've worked on, so it's Earth-like rocky worlds, mainly. And my interest in that is the same as members of the public, which is that those are most likely to harbor the sort of life we know. So this lecture has 4 parts. One is to talk about the classification, the different kinds of atmospheres out there, then structure of atmospheres, and in particular, talk a little bit about stratospheres, and then atmospheric chemistry in a nutshell, and a brief application to biosignatures. So why do we care about composition? Well, I care most because of habitability for the rocky worlds, and basically the composition sets the radiation, sets the climate, sets the albedo. And what we're looking for is worlds that have liquid water on the surface, and you can be too cold or too hot. Composition is also determined, at least for the Earth, in large part by biology. Life dumps waste gases into the air. So here's a cow, and here's some grass, producing oxygen and methane, respectively. And you can think of it, at least for the Earth, it really is an inorganic extension of the metabolisms in the biosphere. So life, along with geophysics, affects the atmospheric composition. And these kind of things also are the biosignatures that in the long-term future, particularly things like LUVOIR and HAVEX that were mentioned earlier, that one wants to look for. The obvious ones, like methane and oxygen, but maybe there are others, and these also affect atmospheric structure. So there's different ways of looking at them. And then there are also anti-biosignatures, gases that are microbial food, but could remain abundant if no one is home. This is like an experiment I do after Halloween, where I have excess candy bars because nobody showed up, and then I leave them out, and if they don't get uneaten, then there's no grad students around. And if anyway, you get the idea. Biology abhors a free lunch. For rocky planets, a big don't know is, obviously whether there's exoplanet life. And this is the same order of question as 30 years ago asking if exoplanets existed, where some people would say, oh, they would just have an opinion about it, not really based on much, but they would say, oh, I think they're common, or I don't think they're common at all. And now we have data to show that they are common. But actually, microbial biospheres, for all we know, could be quite common on the rocky worlds out there. We just don't know. And this may be a technology limit. And an analogy might be microscopic observations, like the first ones done by Anton van Leeuwenhoek. Here are his diagrams, the first person to see microbiology, whereas previously it was completely unknown. And maybe exoplanet life is like that. By the way, his paper got rejected. And it's actually one of the worst rejection letters in scientific history because they said that it caused merriment and considerable giggling. And the secretary of the Royal Society even questioned the sobriety of the observer during his observations. He discovered microbiology. So that's an example I use if a student gets a paper rejected. Don't worry about it, it just means you're doing something interesting. Another end member that it might be common is that Earth is alone, of course. And so that's why we're particularly interested in this don't know question. But when we think of Earth, there are some people with Nobel Prizes who say that particular structures of terrestrial biochemistry and metabolic waste gases, or the food, might actually be predetermined by a planet's geochemical context, the universality of the periodic table, kinetics, redox, affinities, orbitals, etc. So that's something that people in the origin of life community are interested in this question, and that they may be coming at it from a computational chemistry point of view, whereas in planetary science, we're looking at it from an observational point of view. So we have composition, and this sets the chemistry, also the kind of aerosols that may occur. They could be cloud particles, they could be haze particles, and this determines the radiation and structure and the climate of a planet. And life can interfere with these things. So first of all, then, how do we classify atmospheres? What's their sort of taxonomy, naming them, or putting them in groups? And then what can we say about the chemistry-radiation connection? I think it's probably useful to think in terms of physical classification and chemical classification. And the way I look at it, there are sort of two kinds of atmospheres. There's collisional ones and ones which don't have collisions. And frequently, certainly in planetary science, people who are concerned with thick atmospheres will refer to these sometimes as airless bodies, even though they actually have exospheres around them. And then there's some bodies that, why Callisto should have a collisional atmosphere, I'm not quite sure. It's a bit of a mystery. That was reported a year ago. And Io, it's a bit more obvious that where it has volcanoes, it can be collisional, but elsewhere it's collisionless. What we don't know is the distribution of airless versus thick atmosphere exoplanets, and bulk density is a bit of a blunt instrument in this regard. So how that is going to be determined is going to be a lot of spectroscopy, but very important for understanding atmospheric evolution. There's also a physical class on its own, which I call them Clausius-Clapeyron atmospheres. These are atmospheres where basically the whole atmosphere is in equilibrium with the surface. And we have some examples in the solar system. Nitrogen atmospheres above nitrogen ice surfaces, Triton and Pluto are those examples. It definitely isn't in equilibrium. What I mean is that if you have this is temperature, and this is pressure, there is a curve where this is vapor, and this is, it could be liquid or solid, but for these objects, this is the Clausius-Clapeyron equation. And because Triton has nitrogen ice, the vapor you get is set by the surface temperature. So if this is the surface temperature here, then you look up the vapor in equilibrium with the surface, and this will be for Triton in this range here. And if you look at it for Pluto, it should be about 10 microbars. So all it is that the whole atmosphere is being set by a vapor-solid equilibrium. And the same for Mars, in the sense that the polar ice caps are about 148 Kelvin. At that temperature, you get 6 millibars of CO2. So there's also a buffer going on there, and I would put this in the same class. Let's call it a Clausius-Clapeyron. This is not a standard term. It's just one that I've made up, but it makes sense.
So why is there a question mark?
Oh, well, because there's also this alternative point of view that if liquid water appears occasionally, it will suck up the CO2 and react with the surface rocks and make carbonates, and that would tend to draw it down to the triple point, which also is 6 millibars.
David, I
Yeah. Well, that's really a different issue, talking about the total mass. All I'm talking about is given a surface temperature, you can predict what the vapor is. What happens is that there's seasons, so the poles wax and wane. There's a permanent south polar ice cap, but the average pressure is about 6 millibars, roughly. So the mass varies by about 30% because of seasons. So what we don't know, do these kind of things exist on exoplanets? And I would wager they probably do, because we've got more than one example in the solar system. It seems almost inevitable that there are some planets out there with surfaces of a particular volatile, and all you'd have to know is the temperature, and you'd be able to read off the pressure of whatever volatile it is. So what about trying to think about these different atmospheres and how to categorize them? You could group according to some dominant gas, Earth and Titan, Mars and Venus, but I don't like that. Bad student essay, 6 out of 10. Instead, a way I would prefer to think about it is more chemically based, and along this track that we know that certain compositions of atmosphere, like this one, will consist of hydrogenated gases, and hydrogen itself, and these are reducing. And then there are other compositions of gases. There might be minor reduced gases, but they're oxidized carbon or oxidized nitrogen. And these are more oxidizing, weakly reduced, because there's a little bit of reducing gas in there, but basically reducing and oxidizing. And that seems to me like a fundamental division. And so that we can talk about reducing atmospheres like Titan, the giant planets, the Earth, before it had a lot of oxygen in it, maybe Mars, sometime in the distant past, and oxidizing atmospheres, the Earth today, Venus. Venus is always the problem child of the solar system, but at altitude it's oxidizing anyway. If you get near the surface, it's a bit more reducing. And Mars, CO2. Why is this a useful way to think about atmospheres? Because it indicates the chemical character. So you know that in an oxidizing atmosphere, carbon is going to be CO2. In a reducing atmosphere, it'll be CH4. It could be CO if it's a hot Jupiter or something, if the equilibrium shifts it in that direction. And it also allows us to make predictions about the aerosols, right? So if you're in this kind of atmosphere, you'll have certain aerosols, and this kind, you'll have other kinds. Now, I just want to mention the difference between a haze and a cloud, since I'm on the subject of aerosols. So when we look at the solar system, we see two planets, two objects, Titan and Venus, that are completely covered in, we would call them clouds for Venus. We call it a really thick haze for Titan. But when we look at the Earth, we just see these patches of clouds, right? So what's the fundamental difference there? The fundamental difference is that on Titan and Venus, it's photochemically produced. You're producing the H2SO4 on Venus through photochemistry. You're producing the haze on Titan through photochemistry. And because that's happening over the whole body, then you can get this whole cover. But on the Earth, you've got convection, lifting water vapor, and then it condenses out, and you've also got places where it's drier. So a useful way to divide these two things is a haze is a photochemical product, and a cloud is not. It's some supersaturated constituent that forms particles. However, if you go to the terrestrial literature, beware that meteorologists define a haze by size of the particles. So if it's less than if it's of the order of 0.1 microns or something, that's a haze, because it's based on size. But I think from a planetary atmosphere's perspective, this kind of division makes a bit more sense. Yes?
So then for Venus, it could be both. The sulfuric acid is,
Yeah,
right? Because the upper cloud up there is photochemical, but down below it's more patchy and very.
that's right. Well, as I said, Venus is always the problem child of the solar system. Yeah. So how does this lead to things about you can predict? So if you're in a reducing atmosphere, cold and reducing, like Titan the giants, then you know that photochemistry is going to break down the hydrogenated compounds, and then their free radicals will join together to make hydrocarbons. The same occurs in the giant planets. There's some other species, though, that can make other things that are interesting on the giant planets. One key difference is that Titan's very small, so hydrogen escapes, and these products eventually sediment onto the surface. But on the giant planets, these things can be recycled through deep convection or sedimentation, and then at high pressure and temperature, the hydrogen can be added back on again. So you've stripped the hydrogen off with photochemistry, but now you can add it back on, so there's a big circle going around here. But there's still things we don't know. How about a 400-year-old mystery? Why do we have a great red spot? What is the red chromophore causing that? Maybe it's related to photochemistry, UV, case of epic sunburn. What about these oxidizing atmospheres? Well, if they have sulfur in the atmosphere, instead of ending up in the way that it does here, in the form of hydrogen sulfide and maybe polysulfur and various other sulfur compounds, it will be the oxidized form, so it'll end up as H2SO4. I got this picture off the web, and it looks like a shuttle picture, but I'm sure it's been photoshopped because this haze just looks too good. But this is called the younger layer, and it's 20 to 25 kilometers, and basically it's particles of H2SO4, and it contributes about 1% of the Earth's albedo, so it can modulate the Earth's albedo if there's a big volcanic eruption, such as Pinatubo, for example, which cooled the Earth. And on Venus, S is in the air, is SO2, and it's third in abundance after these two other gases, and you get a thick haze, which thick enough to be called clouds in the lower part of the atmosphere, which is very important in the thermal infrared, near infrared, dominates the visible albedo. It's also sort of an anti-biosignature in some ways, because it means instead of the S going into an ocean, or an anti-habitability signature, instead of the S going into an ocean, which is where most of our sulfur is on the Earth, second most abundant negatively charged ion in the ocean after chloride, it's up in the air on Venus. Mars, it's in the soil. It's not in an ocean. It's not in the air. It's in the soil. But there may have been a haze on early Mars when it was volcanically active, and it would have added a significant albedo, so it doesn't help with warming early Mars if that's your game. It's photochemical, in that general classification, but lower down. It can certainly be affected by the issue of saturation or not saturated. So it's one of those awkward cases. Yes? Well, that's the whole topic of atmospheric evolution and origin and evolution. So I'm dealing with that one in a separate lecture. But yeah, come back to that one. So we're all on the same page of music. Just some very basic stuff. This is our mixing ratio, which is moles, but we can also use partial pressures, volume mixing ratios, number densities through the gas laws. And for the Earth, we define it as a dry mixture, but we have to bear in mind that H2O can be extremely variable, and this may be true in some other atmospheres. And then for virtually, for the planets of the solar system, except when you're going very deep into the giants, the ideal gas is pretty good, which we usually express like this. So here's some things we don't know. While the redox division should be universal, there might be some quirky cases where it might be oxidized at the top and reducing at the bottom. We don't know the range of atmospheric compositions, but they're desperately needed if we're to understand the visible infrared transmission properties and even basic properties such as the heat capacity, specific gas constant, and so on. And we don't know the range of aerosol chemistries where we lack the solar system examples. You can hypothesize them, but they need to be detected. And we also don't know the optical properties of unusual haze particles because nobody's bothered to measure them in the lab. Why would they if they're not known to exist on current objects? And this even applies to the early Earth, where we don't know some of these issues. And here's an example of an attempt to try and put atmospheric compositions in context. This is one by Jeremy Leconte and Francois Forget. But really, it's just a cartoon saying, well, if you're really hot, you'll eventually melt on your rocky planet, and you'll have a silicate atmosphere. If you're cold and you're a high mass, then you're going to be up here, a hydrogen helium. So this goes a little bit to the question that was asked. But it's just a schematic diagram, and where these lines are drawn is just made up. But that's where we are. So it's your job as the grad students to figure this out. Okay, structure of atmospheres. So we have to start with the Earth, because the terminology we use for the Earth's atmosphere was developed in the early 1900s. And it's what we use for other atmospheres. That may mean that sometimes it's not very good, because the planet doesn't have a stratosphere, so to speak. But usually there's a troposphere. So here's the Earth, and here's the layers of the atmosphere. And here's also the composition with altitude. And here's some various objects that you might find at these altitudes. So we have cooling in the convective part, the troposphere. We have a stratosphere because of ozone. And then we have cooling in the mesosphere down to the coldest point in the atmosphere, the mesopores. These are the spheres, these are the pores. And then basically, more or less everything can absorb extreme ultraviolet, and so we have a hot thermosphere, and then the exosphere where we have escape of hydrogen and helium. But bear in mind that, things like the space shuttle and some other satellites are actually orbiting in what we call the thermosphere. So that actually is good because it enables us to get a bit of information from satellite drag and that kind of thing. But this terminology doesn't always work very well. So usually, at least on a rocky planet, we expect there to be a troposphere. There might be a stratosphere if there's a shortwave absorber. There might be a mesosphere. There could be a thermosphere, and there should be an exosphere, which is defined as to when it goes collisionless. You could have neither. So in a classic just radiative, this is temperature, and this is altitude or log pressure going in that direction. And in the classic object that doesn't have a stratosphere, you have a convective troposphere, and then it goes isothermal, where it's radiatively dominated, right? And there's no shortwave absorber here. So a pure CO2 atmosphere might look a bit like this, right? So you don't... Well, so people vary. They'll certainly call this a troposphere, where it's convective, and they will either call this a stratosphere, even though there's no absorber, or they'll call it a middle atmosphere, right? So that's why these names developed in the early 1900s don't always work very well for other planets. But if there is, certainly if there is a point of inflection here and you do have a stratosphere, then this will definitely be called a stratosphere. And it won't be called a middle, well, it could be called a middle atmosphere, but you'd usually call it stratosphere. So to discuss that a bit more, so thinking about why and how tropospheres cool with altitude, that's obviously convection when you have a warm surface underneath. But what we know is that we can get that in a dry atmosphere just through very simple parameters, the gravity and the specific heat capacity, which is easy to remember for Earth. It's just G divided by 1,000. But when we look at the atmospheres of the solar system, this is not what we see. We hardly ever see on average an adiabatic lapse rate. We see that it's less, the decline in temperature with altitude. And that's because everything contains condensables, or in the case of Mars, dust. And these things, by releasing latent heat, will change this profile to be different, or by absorbing solar radiation. And usually the factor is somewhere between 0.6 and 0.9. The stratosphere warms with altitude like this, and it peaks at about 50 kilometers. Ozone itself peaks about 25 kilometers. Why are they different? Why is the peak heating not at the peak ozone? That's not really the answer. It's not really the answer. You think of what are you integrating to get heating? You're integrating the abundance of ozone, but what else is there? Well, it's also a function of the spectrum, right? So higher up, you've got more shortwave photons. And so it's an integral of all those things. And that's just the way it works out, is that even though it peters out the ozone as you go up, you're thinking about also the range of photon energies, which are going up a lot as you go up. And what's the coldest point of the atmosphere? On the Earth, it's the mesopause, so it's the top of the mesosphere. Do you think there might be a similar cold point in other atmospheres? And here we have to think about, why do we have a mesopause? So the mesopause is because radiative cooling from carbon dioxide. Okay? So that's what's causing that. And this is competing. Radiative cooling is being competed against a redistribution of energy by collisions. So at some point in an atmosphere, collisions will become ineffective. And if you've got a radiatively active gas, that's still up there, it will be very effective in cooling that part of the atmosphere. So having said that, so who thinks there will be a similar cold point in other atmospheres? And who doesn't? Hands up those who think yes. Hands up those who think no. And everybody else is abstaining. Well, the abstainers are right, because sometimes you do and sometimes you don't. So actually, it's an issue of debate even for Titan. So Titan looks like maybe it has a mesopause, and it's not the coldest point, though. It is a cold point. But it's not as cold as the stratopause. And Jupiter probably has a mesopause, but the other giant planets, we're not really sure, partly because their profile's not as well understood as Jupiter's is. And if you don't have the right radiatively active gas, then you probably won't have one of these things. So it depends on the composition. But you will have collisions will deplete, and eventually, if you do have a radioactively gas, an appropriate one, then you would have a mesopause. I think that's the way to frame it. It's conditional, it could happen. Peter's looking.
I'm just thinking, because the radioactive gases, as far as I know, are those that have a dipole, like CO2.
Well, it's not strictly true, but
Okay.
it is in general, yeah.
It's easier that, but if you have something like O2, which is symmetric, or H2,
Right.
it will be harder to lose. So I'm just
That doesn't work, so you have to, because remember the H2 absorption comes from, I haven't covered this yet, collision-induced absorption, which relies on collisions.
So that, yeah, exactly. So in an area of the atmosphere where they're not colliding, they're
Yeah.
holding on to the heat. So I'm just thinking
So
about times they're all
in a reducing atmosphere, you need something like acetylene or HCN or something like that, ethane, something that can be radiatively active and cool if there's enough of it up there, right?
Now, I'm thinking in terms of the giant planets all have plenty of hydrogen. So as you go up into the atmosphere, it will become more and more this H2
Mm-hmm.
and stuff. So it'll be hard to figure out why they wouldn't have that.
Well, I mean, they can cool further down where it's collisional, and the hydrogen collision-induced absorption does cool in the stratosphere of, it's a radiative cooling term, because it's radiating through a fairly transparent region at that point.
I guess I'm arguing that they would not necessarily have I mean, I'm just saying at some point the temperature will start increasing because you're not cooling, right?
Yes.
So,
A thermosphere.
There's your lowest temperature, and that would
Yes.
so much.
Well, not necessarily. Not if there's enough radiatively active gas, right? It could just be isothermal and then become warmer. Earth to high altitudes. So this bit is mixed below about 100 kilometers, and above we have a separation by diffusion and by species, so that if you go up high enough, hydrogen will become the dominant component. But if you look down here, nitrogen and oxygen are well mixed. This, of course, this high temperature occurs because it's just looking at the speed of the particles, and a lot of things are absorbing in the EUV, and they can't thermalize very easily. But one thing we don't know is why thermospheres on Jupiter, Saturn, Neptune, and Uranus are so hot. So if you do the calculation with just solar energy absorption, you'll get a really bad answer, especially for Jupiter. You'll be out by about 700 Kelvin. You'll get an answer of 200, and it should be more like 1,000. So what's the reason for this? And the reason is not fully known. And it thought it might be to do with dynamics, so buoyancy or gravity waves propagating to the upper atmosphere. It might be to do with the magnetic field, auroral energy being produced, but not fully known. And it's useful to know that you have this kind of mixing up to 100 kilometers on Mars, Venus, and the Earth, because sometimes you run across papers like this one in Nature, which argued that the ancient Earth's atmosphere was stratified in bulk composition, with about 20% oxygen at 80 kilometers and less than, through other constraints, a part per million of the ground. And you have to ask yourself, is that possible? Because what's causing this is turbulence, right? And what's causing the turbulence is all of the things that happen in the atmosphere dynamically, so the waves that propagate upwards and so on. So anyway, I would suggest this paper is a bit questionable.
It could be atomic oxygen, but if you have an Eddy diffusivity less than 10 degrees.
Okay, but you've just lowered your eddy diffusivity below
You have to.
below normal values by what, 2 orders of magnitude? I don't like lowering turbulence by 2 orders of magnitude for no reason, because real atmospheres, we all know if there's flow over topography, it generates buoyancy waves. They propagate upwards. They deposit a lot of energy at the top. They mix things.
I'm aware that Eddy diffusivity, which is what we're talking about here, is a parameter for chemical models.
Yes.
It doesn't have any real existence. We try to tie it to turbulence, then you can do that in a convective fluid, say, where turbulence is an accurate description of what's going on. But the stratosphere is not turbulent.
Well, you have to resort to 3D GCMs, and yeah,
That's all subscale motion.
right.
You still can't do it.
Well, you can for the large scale if you can connect the large scale down to the eddy diffusion parameters.
You can get cascade.
Right. Atmospheric structures. So I looked at Earth, and now let's look at the other planets and Titan in the solar system. And you can see the tropospheres and stratospheres, except for Venus, which doesn't have a stratosphere because its CO2 is not a very good shortwave absorber. And as Jonathan mentioned, there's ozone causing this, and then there's hazes and also some absorption in the near-infrared by methane for the outer planets. Some time ago, while teaching these kind of things and putting up these kind of graphs, we noticed that there was a common, roughly within a factor of 2 or 3.1 bar tropopause, which is this turnaround from the troposphere to the stratosphere. And the reason for that is related to radiation. Basically, all of these atmospheres are, to first order, infrared, thermal infrared opaque at depth, down at, say, 1 bar. But the absorption of infrared photons depends on pressure in a couple of ways. Pressure broadening, when collisions take or add energy and broaden, they allow a bigger range of infrared photons to be absorbed. Or, as discussing earlier, collision-induced absorption, sometimes abbreviated to CIA, not to be confused with the intelligence agency. Collisions distort a molecule's electronic structure, and they can cause a temporary dipole or quadrupole or something. And that's why hydrogen is a greenhouse gas on the giants and on Titan. And these have the same kind of pressure dependence, where the optical depth depends on the pressure squared. And so as you go from the optically thick, opaque part up to the optically transparent, they reach a similar kind of pressure where the air is transparent enough to infrared the short wave, the visible, or the ultraviolet heats and makes a stratospheric inversion. So these kind of principles, because they're basic physics, they're going to be the same on exoplanet atmospheres. And so whether you see an inversion or not tells you something about the ratio of the infrared optical depth to the shortwave optical depth of what's ever there, right? And to go into more detail, to take Earth as an example, we have an ozone layer. This is important for habitability because it protects the surface from harmful UV. That allows us. It's pretty bad today, but we don't get sunburn in tens of seconds, severe. But it's bad for Mars, which doesn't have an ozone layer and gets sterilized daily. For the Earth, this happened. This ozone layer was built about 2.4 billion years ago. So if you were an astronomer looking at the Earth before that, you just wouldn't see this kind of structure. And well, you can tell these are harmful. All you have to do is just compare Planck's law with the bond strength of carbon in organic molecules. The abundance of ozone is very nonlinear with respect to how much oxygen you have around. The reason for that is that when you make ozone, you photolize an oxygen molecule, you make an oxygen atom. That oxygen atom has to join with another oxygen molecule. You now involve 2 oxygen molecules, so you wouldn't expect it to be linear. So this is the column, molecules per square centimeters versus present levels in the Earth's atmosphere of oxygen. And you can see this non-linearity. Here's today's ozone layer, peaks about 25 kilometers, 10 parts per million, which is as I mentioned earlier. And we've known how it works for a long time. And I'm coming to why this is important in a minute for detecting certain things on exoplanets. But we have to know that this comes from chemistry, which is basically photolizing oxygen and that combining to make an ozone, And then the ozone does its business in protecting us from UV, but you can get rid of the ozone like that. And these are the Chapman reactions figured out by Sidney Chapman in the 1930s. And basically then the ozone does a dynamic, is set to some dynamic abundance. Now there are also catalytic reactions that modify this, but this is a pretty simple scheme to understand, like that. And if you calculate it, you overestimate it because you haven't considered the catalysts. Here are the various catalysts. One thing to note from this is that these kind of atoms, or things that have a spare electron, are free radicals. And it's free radicals that are driving the chemistry of atmospheres. You see the ozone layer frequently in the evening. And here's the way you see it. Because it doesn't just absorb ultraviolet, it absorbs in the visible, particularly in the yellow, orange, at about 600 nanometers peak. These are the Chapuis bands. And so here's a simulation with ozone and no ozone. So when you're going through very large path lengths, the ozone is taking out the yellow. And so if you did this using transmitted starlight for an exoplanet, you could hence deduce ozone, hence deduce oxygen, hence, and then speculate about oxygen producing life to get your paper in Nature, which may be rejected. So just some basic concepts, optically thick and optically thin, which we've been bandying about. I suspect most people with an astronomy background know what we're talking about, but when you have some light that's coming from over here, I think, maybe you have to press the button again. Try that. Movie's not working. Oh, and so there it's being absorbed in the optically thick case. And in the optically thin case, it's just passing right through because it's transparent. These are just fancy words that the scientists use for opaque and transparent, basically. But except we can quantify it in terms of 1 or a lot greater or very much less than 1 when we have a Beer's law type relationship. But this relates to atmospheric structure because down here you can be optically thick, so you have a convective profile. You drop below unity, or in some cases bigger if there's a lot of absorption of shortwave. Then you'll become radiatively dominated up here, but you still have to go some way up before you have enough and become very optically thin in the infrared before the shortwave dominates. Okay? So this is how this system works. And it's driven by these fluxes of thermal infrared, shortwave radiation coming in, being absorbed, and you can play with the internal heat. And I'm not going to talk about it, but if you play with the solar flux a lot and step it up and have a heavily irradiated planet, or play with the internal heat a lot, of course you could get different structures. So I know Jonathan Fortney, for example, has looked at heavily irradiated planets and having a so-called detached convective layer above a radiative layer, and then further down, convective again. But this is the way that we can model that. One thing we don't know, remember there's some anti-lecture material here, we don't know the possible atmospheric structures and the extent to which they mimic what we have in the solar system. Okay, we have HD, what's it called, 2984, I've forgotten the number, for something B, right? Doesn't have a stratosphere, but what about all the other ones? So we don't really have the same kind of information that we have in the solar system to really deduce how general this is or how unusual. So that was atmospheric composition, that was atmospheric structure. Now I want to turn to atmospheric chemistry in a nutshell. And there are two approaches to chemistry. One is thermodynamic equilibrium, and you can think about this as what should or can happen if everything reacts to equilibrium. And there's kinetics, which is what actually happens. And that depends on reaction rates. And thermodynamic equilibrium is when forward reactions equal reverse reactions, and it's not too awful. What you calculate, if you're dealing with a high pressure and temperature case, or a case where everything gets convected to high temperature and pressure regularly. So people do thermodynamic equilibrium models for Jupiters, hot Jupiters, and so on, and they're not too awful. You can also, by comparing the equilibrium model with reality, or with the kinetic model, you can figure out what species are in disequilibrium, and that might tell you something about profound, perhaps, about either the circulation or the chemistry or something else. And these models, they basically minimize Gibbs free energy. Gibbs free energy, if you can't remember your chemistry, is useful energy to do work, as opposed to thermal energy dispersed in this floor, which is pretty difficult to extract to do useful work. So a way to represent this is with this kind of diagram. Here's the Gibbs energy, and here's a reaction that actually works because the delta G is negative. That means it should and can happen. You can go downhill. But you have to overcome an activation energy, and this depends on temperature. So what should or can happen may not happen, and frequently doesn't. Here's an example of what I've called hash thermodynamic equilibrium fail, a well-known hashtag. And here's methane and oxygen reacting. This is just combustion. And what you can do is you can calculate, say, at 25 degrees Celsius, where we can readily look up these numbers. We can calculate the Gibbs free energy change of reaction by looking at the products minus the reactant sums. It comes out negative. Yay, it should go, right? This is thermodynamically favored. We're rolling downhill. And you can calculate the equilibrium constant, and it's really big. That's a really, really big equilibrium constant. Basically, it should suggest that everything should react to CO2 and H2O, and you'd be left with hardly any of these reactants. So in our own atmosphere, how much methane should coexist with 0.21 bars of oxygen and 400 parts per million of CO2, which is what we currently have, keeps going up. So you can write down the equilibrium constant can also be written as the products of the reactants divided, products divided by reactants, and then rearrange that, and you figure out that the partial pressure of PCH4 in equilibrium with this is 10 to the minus 145 bars. Okay, there's 1 bar, so that's also a mixing ratio, but there's only 10 to the 44 molecules in the Earth's atmosphere, so there'd be less than 1 molecule by a considerable factor. But there aren't. There isn't a complete depletion of methane. That's because Earth's atmosphere is kinetically dominated. And thermodynamics works really badly for cold, rocky planet atmospheres. The methane is pumped out by biology. It's in a dynamic balance determined by kinetics. If we work out say, let's just take a mole of air for the Earth and react it to equilibrium. And let's take a mole of air on Jupiter, a mole of atmosphere, and react that to equilibrium. And figure out how much useful energy we can extract, the Gibbs free energy. Call that delta G. The thermal energy is RT per mole. Divide by RT, make it non-dimensional. And we plot that out. We can see that the Earth stands out. This also includes the fact that the Earth's in equilibrium. We add another fluid beside the gas, which is water, can take place in our equilibrium. Mars is pretty high, and only really about an order of magnitude smaller than the Earth. And the reason for that is you've got a thin shell of air around the planet on Mars, and you can do quite a bit of photolytic damage to that atmosphere, and you can create from the carbon dioxide carbon monoxide and oxygen. Well, that's a disequilibrium pair. They should react together, right? So this is abiotic disequilibrium we're looking at on Mars, driven by photochemistry. And it makes an important point, which is that all atmospheres are in chemical disequilibrium to some extent. They must be because they're receiving free energy from starlight or sunlight, so they've got an input of free energy which is going to drive some disequilibrium. They may also be driven by energy coming from the interior into disequilibrium. But that's abiotic disequilibrium, and the disequilibrium we have on Earth is dominated by oxygen, nitrogen, and water, because the nitrogen and oxygen and water would like to be nitrate thermodynamically. There's a bit of disequilibrium from oxygen and methane too, of course, but there's not much methane. So in terms of joules per mole, it's not that much. So Earth stands out, and this may be, this metric or others like it, may be a way in the distant future, in the 2030s, when you're still active in your careers, and I'm like getting, me and Jonathan are getting towards retiring, or maybe even retired, depending on mission delays. These kind of metrics may be, once you've got a spectrum and able to figure out the gases, you might think about this in terms of a way to determine whether it's a living planet or a dead planet, to distinguish between biogenic disequilibrium and abiotic disequilibrium. Kinetics, of course, is what you'll have to understand as part of this. So this is just looking at it from thermodynamics. Kinetics potentially provides a more powerful tool. So in kinetics, we have a couple of things reacting. They go to a transition state, which is always marked with an asterisk, and then the products. And this reaction rate is going to depend on how much stuff is there. And then you have a reaction rate with some coefficient, and these will be to some power. That could be unity. But basically, the thing about kinetics is it's all laboratory-based. This rate coefficient has to be determined in the lab. These exponents have to be determined in the lab, at least today, unless computational chemistry, quantum chemistry improves to the point where people can make reliable predictions about these things, but I don't think it's at that point yet. And photolysis is also similar, that you've got a rate now. This is the R that was on the previous thing. And here you've got some photolysis coefficient. And the thing is, though, is that this doesn't all go to the product. Sometimes it can do other things. So there's an efficiency factor that has to be taken into account. So the rate of absorption processes, the absorption cross-section, the fraction of dissociation that gets what you want instead of these other pathways, the quantum yield. And then you can write down what the J should be from an integral over the actinic flux, which that's a term from photochemistry. It means the solar photons that are acting on a volume to drive the photolysis. So these things. That's from the lab. This is from radiative transfer calculations, and this quantum yield is from the lab. But supposing we want to know whether a kinetic reaction works, well, we're back in the old realm of thermodynamics. And since you're talking about bond breaking and bond formation, heat release or not, you can actually use enthalpy as a pretty good guide rather than Gibbs free energy in this case. So for example, photolysis of ozone. To make ground state oxygen, you look up the enthalpies of these various things. So this would be the products minus reactants. You get this value. If you convert this by Planck's law into a photon wavelength, then you'll see that this reaction can take place out to quite long wavelengths, about 1 micron. And that is related to the ozone absorption by the Chapuis bands that I mentioned earlier, when you see ozone in the evening through its absorption of yellow light. But ozone can also be photolysed if you have energetic enough photons to make, this is an excited oxygen state, O singlet D. And I'm not going to explain this term symbol thing because it's quite complicated dealing with lots of quantum numbers. But I can give somebody a handout on that, which I have for my class, which runs over several pages. But, and actually, Hertzsprung was responsible for these terms, symbols, and he was an astronomer, so just blame your colleagues. So if you do the same calculation for this, you'll figure out that the wavelength cutoff is 340 nanometers. So you can use thermodynamics to say useful things about which reactions, whether they'll work or not. And there are some reactions that you can propose, and then you do the thermodynamics, you realize, oh, that's never going to work. And there might be some reactions proposed in the literature where you do the thermodynamics, and you realize, oh, they made a mistake. That doesn't work. Because they didn't bother. The other important point about atmospheric chemistry is its free radicals do everything. So free radicals are these unpaired electrons, yeah?
Just actually go back to the ozone analysis. What I never understood about columns is why there could be distinct bands like this. Like, why doesn't a photon at 400 or 380 nanometers just destroy ozone even more than one at 600? So why is there a gap there?
Oh, that's a good question.
Why doesn't it all just continue upwards from the place where it can be destroyed?
Well, yes.
So then if that photon strikes the molecule, what happens? Does it just visibly scatter?
I mean, this structure here is, like people said, comes from, the allowed quantum states, which is why you have all these little bumps. And if you looked at it more, it would be even bumpier. So, so that's why it basically doesn't do that. It's not accessing the quantum states here. But as far as we're concerned, this is not calculated. It's just something that's a laboratory measurement done at a bunch of different temperatures. So free radicals are these things with unpaired electrons. They also include the oxygen atom, which has or things with lone pairs, sort of called biradicals. And basically, when radicals react with non-radicals, like, say, a molecule of oxygen or a molecule of CO2, they'll always generate more free radicals. And then those free radicals can generate more in a chain reaction. But a radical plus radical reaction makes a non-radical and ends the chain. So this is how photochemistry works. Let's think about this by trying to summarize the Earth's photochemistry in a single diagram, which I've tried to do here, or at least capture the important points. There's a lot of other photochemistry that goes on on the Earth, but this, I think, is the two key issues. And the two key issues about the Earth is that it's wet, represented by my ocean here, and it's oxic, it's full of oxygen. So when you have lightning in an oxygen-nitrogen atmosphere, you can make nitric oxide, or nitrogen dioxide can be oxidized to this. If you photolize that, you'll make a ground state oxygen atom. It can react in the troposphere to make some ozone with the oxygen. The ozone can be photolized at those short wavelengths, 340 nanometers, to make excited oxygen, because that's the 340 nanometers is still getting through the ozone layer above some of it. That then reacts with water, it's a wet atmosphere, to make OH. And OH is the Earth's detergent. It goes around and it clears up all the muck. And the muck are things like methane and organics, literal muck, but also ammonia, carbon monoxide, H2S, SO2, and NO2. And we should be grateful for OH, because if it didn't go around being a detergent, this stuff would build up, and it would smell really bad. There's another factor here. The water also allows rain, so when these become oxidized and soluble, like H2SO4, that can rain out. Or ammonium sulfate rains out. Ammonium sulfate is also a cloud condensation nucleus. So the keys to understanding how the Earth chemistry is working is that it's an oxygen-rich atmosphere and a wet atmosphere. And that makes this free radical, particularly abundant. It's actually not that abundant in number, but it's relatively abundant compared to what it would be without the ocean existing. And this was only figured out in the 1970s, actually, this reaction being a key to the Earth's atmosphere. And it makes the Earth's makes Earth the sunniest planet in the solar system in terms of the flux to the surface with an atmosphere. And it makes the air transparent to visible because you clean out this stuff. And if this stuff wasn't cleaned out, it would make a nasty haze somewhere, probably at high altitudes. So that's what makes the Earth quite different. And this is important for astronomy because the fact that you've got the water and the oxygen. Remember, what's making the oxygen is this green stuff, and the water is from having a habitable planet. But when we look from a distance, we see Earth as a pale blue dot, as Jonathan showed. Why is it a pale blue dot? It's a pale blue dot because we're looking at the way this chemistry is reflected in literally reflected light. We have a transparent atmosphere that makes it liable to do Rayleigh scattering instead of having a hazy atmosphere which would look orange. Or maybe like Titan. And in detail, when we look at the shortwave reflected spectrum of the Earth, we see the Rayleigh scattering. This is the blue. We see a U shape where there's ozone. This is the Chapuis bands absorbing the yellow, orange. And then there's also something else going on here, which is vegetation and continental surface. But the pale blue dot, Rayleigh scattering, clouds, minor ozone absorption, makes us pale blue. So understanding the chemistry of an atmosphere is going to be essential if you really want to have deep knowledge of what it is you're looking at astronomically in direct imaging. And that pretty much concludes what I'd like to say. So let me just summarize what I've said so far. I suggested that compositions that we know could be divided into chemically reducing with organic hazes, hydrogen-rich, and hydrogen-poor, oxidizing, with sulfate hazes, which can be global cover, Venus, or extremely thin on the Earth, or absent, Mars. But maybe there was a haze on early Mars. The unknown, the big unknown, is the zoo of exoplanetary atmospheres and how, whether they fit into this kind of scheme of things or it needs to be more complicated. I mentioned how reducing atmospheres we know have stratospheric inversions from the absorption of shortwave by hazes and a bit of methane. And you can also get stratospheric inversions in oxidizing atmospheres like the Earth, but Venus doesn't have one and Mars doesn't really have one either. Chemistry, all chemistry, atmospheric chemistry, is driven by kinetics, not thermodynamics. Thermodynamics is an approximation which can be very bad, particularly in the case of Earth-like planets. Not so bad for hot Jupiters, perhaps. Applied to the Earth, we see that simple compositional character, if you just knew, if you're looking at the Earth as an extraterrestrial and you just knew that it was oxygen, nitrogen, air, which was wet, you would actually be able to figure out a lot of the key characters of the Earth's atmosphere that set its shortwave transmission and reflectance. So the bottom line is that chemistry and composition lies behind what we observe astronomically. It's worth knowing about. And next time, I'll talk about radiation and climate. Thank you. Questions? Yes?
So you talked about the composition of the atmosphere, and you get the number what it was for ozone. But what's the variability?
Of the ozone, in the ozone layer?
And in general, are you talking about 5% variability, 10% variability?
Well, if you include the ozone hole over Antarctica, then it's 30% variability. But if you didn't include that, it would be probably, I don't know, 5% or something. It would be much lower in natural processes.
And for CO2 and in general, what's the variability on the Earth?
Well, things like CO2 are a well-mixed gas in the troposphere, right? It's a bulk constituent. So it's on annual timescales. Right now we have 400 parts per million in this room, in the globe. And basically it's more or less 400 parts per million everywhere around the globe. There's a little bit of hemispherical asymmetry, perhaps, between the northern hemisphere and the southern hemisphere, and the same with methane, which is another long-lived gas. So what you're concerned about is lifetime of gases, right? So something like methane has an average lifetime in the troposphere of 9 years before it gets oxidized. So a methane molecule hangs around on average for 9 years before being oxidized to CO2 and water vapor. That means it's well mixed because the dynamics, the winds will mix that constituent to be a uniform composition in the troposphere. And the same with carbon dioxide, except carbon dioxide is modulated by the biosphere, so you see a sawtooth pattern as CO2 is taken up in the northern hemisphere growth, and then winter season. So there's a seasonal cycle, but the average globally is a well-mixed constituent. The short-lived constituents, they can have, like SO2 sticks around for a day, roughly. That's its lifetime. Well, that's not enough to mix it. So if you have a volcano going off here, then you can have very high concentrations of SO2 that are 1 million times bigger than over here, where there isn't any volcano. So for the short-lived species, there's big variabilities. Basically, variability is correlated with lifetime. Yes? Yes.
Was that an example, or did you need the lightning?
You need the lightning unless you've got people polluting the atmosphere to make NO2. But basically, well, you can also get some nitric oxide from upper atmosphere ionospheric reactions as well. So that was to make nitric oxide NO, which then makes NO2, and it's the NO2 which mainly supplies the atomic oxygen in the troposphere, which then makes the ozone, which then, what does it do? I'm forgetting my own schematic, but it then basically makes the excited oxygen, which then reacts with water vapor to then make the OH radical, which is the key.
So the question is,
so
that be a very localized thing?
Well, there's lightning happening, thousands of them, every day. So,
right, but in a very small region.
Yes, it doesn't matter though. Yeah, it still is enough to, because it can be mixed. The products. You can also get some nitric oxide from photolysis, probably, of N2O, which is a biological gas, nitrous oxide. But that requires biology. Yeah. I'm going to go to the back first. Yes? Which diagram? Disequilibrium. Oh, yeah, okay, let's go back there. The one with the bar chart, the histogram. Okay, so all we did here was we took a mole of air, say, on Jupiter, 1 bar. Right? We took a 1 bar as being typical. We know that composition. It's been measured by the Galileo probe. We then ran a numerical model to minimize the Gibbs free energy, which is basically reacting everything to equilibrium in that mole of air. From that model, we can figure out how many joules per mole of free energy there is in that mixture. If you were to react it, how much you would produce. Okay? That's what this delta G is here. You don't have to normalize it, but we decided to normalize it with respect to RT, which is just, RT is just the thermal energy, joules per mole in a gas. So if you do that, this is the number you get, taking the known compositions from the Earth, Mars, Titan, and Venus. So for Mars, for example, we didn't use 1 bar because it doesn't have a 1 bar atmosphere. So we took the surface composition, which is 96% CO2, the latest stuff from the Curiosity rover, a little bit of nitrogen, a little bit of oxygen, and so on, a little bit of CO. If you react those things together, you can get about, the number I think for Mars is about 200 joules per mole, off the top of my head. For Earth, it's about 2,000 and something joules per mole. That's why I said there's an order of magnitude difference. But why did I normalize by RT? Well, it's kind of cheating to just take the raw disequilibrium numbers, because some planets are closer to their star, so they're getting more flux to drive disequilibrium. It's really hard to take that out of the equation, so we just said, okay, because temperature depends on a bunch of other factors, not just solar radiation, but the bond albedo as well. But we thought this was a way to do it. It actually doesn't make a lot of difference. If we just plotted delta G on here, it would still look the same qualitatively. Yeah. Mm-hmm. I don't think it's something we're not measuring in the case of ones that are well studied, like the one which Michael Line has studied. I just think, at the moment it's somewhat data limited, but I don't know. I didn't do the retrievals. What do you think, Michael?
We have pretty decent data right now. It's taking an absorption feature in the water vapor things that we rolled out would be that option. But I think there's just something we don't understand about the way the UV photons are interacting with whatever exotic oxides or something.
But do we really have a big enough sample to talk about inversions and not inversions?
What is interesting is with a lot of these hotter objects, more talk about this more. If you look at the thermal emission spectrum, red, it looks like black objects. Consistent with these isothermal atmosphere. To me, an isothermal atmosphere means inversion. There's some absorber that is bringing the temperature back up beyond what you would just get from whatever. So there's some sort of gases that are absorbing, but they're not absorbing to the degree that say ozone.
Okay. Who's going to go next? Well, I guess Colin had his hand up first. Sorry.
It will become isothermal. Yes, so where we're generally probing is where there is a temperature gradient.
Okay. Right.
But if you have a deep enough absorption band, for sure, it wouldn't come.
Okay, where you're falling is deep enough to get radiation would
Yeah,
be.
yeah.
So just that's the weak way of falling. Thanks.
Okay. Yes.
I wanted to ask about your closest atmosphere.
Oh yeah.
Sometimes I think of it as collapsed atmosphere.
Maybe.
So you said that you think some potential be that it's which makes sense to me. I wonder about if you have some thought about what make the distinction between planets that are in that regime and planets that are not. It seems to me that it might be just initial conditions have enough atmosphere, then I will equalize the better by advection, and I will not have the main sphere of the atmosphere. While you have a thin atmosphere, I might be in that regime. Is that just
Well, yeah. I mean, it's certainly true that the Clausius-Clapeyron atmospheres we see are all thin ones in the solar system. They're all cold. But you could go the other extreme and have a runaway. Well, that's only going to be a temporary phase, but a runaway greenhouse is essentially a Clausius-Clapeyron atmosphere where you're getting vapor in equilibrium with the surface temporarily. I think it's only going to work if you've got some single volatile that's dominating the atmosphere. And you could diagnose this because you could measure the surface temperature on an exoplanet, maybe, if it's a rocky planet and you've got a window in the spectrum. And maybe you could diagnose something about a bulk constituent. And if you could do that, and it turns out that the inferences about pressure from looking at constituents and maybe you could figure out that it was a Clausius-Clapeyron kind of atmosphere. But in the case of, it has to be related to having that single volatile. So for the Earth, it's clearly couldn't be because it has nitrogen and oxygen. But for Mars, it could be because there's CO2 is dominating everything. So I think it's to do with origin and evolution, how you end up in that state, rather than a question of atmospheric dynamics or advection.
But Mars was not, when there was water flowing, it was not such a flat atmosphere, only when it was
Only when you got what?
early Mars with water flowing was probably not in that phase.
Right. Whoops, moving too close to the speaker. Yes, but in that case, the volatile on the surface is not the CO2. It's in fact, you don't even have it on the surface. You just have water. So it's not the same case. So there has to be on the surface the same volatile that's in the atmosphere. That's another aspect of the problem. Yeah. A methane-like world? Yeah, there's no reason why you couldn't have a methane world.
Oh, they just assume methane loses a lot of its like dissociation.
Right.
And now work on this other word of
Oh, I see. Yeah, that's a... Yeah, I think that's a different problem, though, looking at methane loss from Titan and transiting to a nitrogen atmosphere. Right at the back. Oh, okay. Yeah, so I was specifically talking about chemical disequilibrium rather than physical disequilibrium. Those things are different. And in the atmosphere, it's driven by the UV and shortwave. You're breaking things up. You're making species that take some time through kinetics to recombine back to where they were or make other products. So that's the disequilibrium, and that is always going to be driven by sunlight. It can be a steady state, like on Mars, there's a steady state disequilibrium of oxygen and carbon monoxide. Those things should react together and make carbon dioxide. That's their equilibrium state. But that's all driven by photons, shortwave. In the case of Mars, that would be driven by photons explicitly under 200 nanometers wavelength, which is what's required to break up CO2.
Did you get a steady state disequilibrium driven by volcanism?
Yes. So if it's volcanically active, that's new stuff coming in, which is out of a chemical equilibrium. Any other questions? Or I'm sort of between you and lunch, aren't I? Which is like that bit in The Lord of the Rings where they say don't come between the, what's it called, Nazgul and his lunch or whatever. Alone, of course. And so that's why we're particularly interested in this don't know question. But when we think of Earth, there are some people with Nobel Prizes who say that particular structures of terrestrial biochemistry and metabolic waste gases, or the food, might actually be predetermined by a planet's geochemical context, the universality of the periodic table, kinetics, redox, affinities, orbitals, etc. So that's something that people in the origin of life community are interested in this question, and that they may be coming at it from a computational chemistry point of view, whereas in planetary science, we're looking at it from an observational point of view. So we have composition, and this sets the chemistry, also the kind of aerosols that may occur. They could be cloud particles, they could be haze particles, and this determines the radiation and structure and the climate of a planet. And life can interfere with these things. So first of all, then, how do we classify atmospheres? What's their sort of taxonomy, naming them, or putting them in groups? And then what can we say about the chemistry-radiation connection? I think it's probably useful to think in terms of physical classification and chemical classification. And the way I look at it, there are sort of two kinds of atmospheres. There's collisional ones and ones which don't have collisions. And frequently, certainly in planetary science, people who are concerned with thick atmospheres will refer to these sometimes as airless bodies, even though they actually have exospheres around them. And then there's some bodies that, why Callisto should have a collisional atmosphere, I'm not quite sure. It's a bit of a mystery. That was reported a year ago. And Io, it's a bit more obvious that where it has volcanoes, it can be collisional, but elsewhere it's collisionless. What we don't know is the distribution of airless versus thick atmosphere exoplanets, and bulk density is a bit of a blunt instrument in this regard. So how that is going to be determined is going to be a lot of spectroscopy. So life, along with geophysics, affects the atmospheric composition. And these kind of things also are the biosignatures that in the long-term future, particularly things like LUVOIR and HAVEX that were mentioned earlier, that one wants to look for. The obvious ones, like methane and oxygen, but maybe there are others, and these also affect atmospheric structure. So there's different ways of looking at them. And then there are also anti-biosignatures, gases that are microbial food, but could remain abundant if no one is home. This is like an experiment I do after Halloween, where I have excess candy bars because nobody showed up, and then I leave them out, and if they don't get uneaten, then there's no grad students around. And if anyway, you get the idea. Biology abhors a free lunch. For rocky planets, a big don't know is, obviously whether there's exoplanet life. And this is the same order of question as 30 years ago asking if exoplanets existed, where some people would say, oh, they would just have an opinion about it, not really based on much, but they would say, oh, I think they're common, or I don't think they're common at all. And now we have data to show that they are common. But actually, microbial biospheres, for all we know, could be quite common on the rocky worlds out there. We just don't know. And this may be a technology limit. And an analogy might be microscopic observations, like the first ones done by Anton van Leeuwenhoek. Here are his diagrams, the first person to see microbiology, whereas previously it was completely unknown, and maybe exoplanet life is like that. By the way, his paper got rejected, and it's actually one of the worst rejection letters in scientific history, because they said that it caused merriment and considerable giggling, and the secretary of the Royal Society even questioned the sobriety of the observer during his observations. He discovered microbiology. So that's an example I use if a student gets a paper rejected. Don't worry about it, it just means you're doing something interesting. Another end member that it might be common is that Earth is but very important for understanding atmospheric evolution. There's also a physical class on its own, which I call them Clausius-Clapeyron atmospheres. These are atmospheres where basically the whole atmosphere is in equilibrium with the surface. And we have some examples in the solar system. Nitrogen atmospheres above nitrogen ice surfaces, Triton and Pluto are those examples. It definitely isn't in equilibrium. What I mean is that if you have this is temperature, and this is pressure, there is a curve where this is vapor, And this is, it could be liquid or solid, but for these objects. This is the Clausius-Clapeyron equation. And because Triton has nitrogen ice, the vapor you get is set by the surface temperature. So if this is the surface temperature here, then you look up the vapor in equilibrium with the surface, and this will be for Triton in this range here. And if you look at it for Pluto, it should be about 10 microbars. So all it is that the whole atmosphere is being set by a vapor-solid equilibrium. And the same for Mars, in the sense that the polar ice caps are about 148 Kelvin. At that temperature, you get 6 millibars of CO2. So there's also a buffer going on there, and I would put this in the same class. Let's call it a Clausius-Clapeyron. This is not a standard term. It's just one that I've made up, but it makes sense.
So why is there a question mark?
Oh, well, because there's also this alternative point of view that if liquid water appears occasionally, it will suck up the CO2 and react with the surface rocks and make carbonates, and that would tend to draw it down to the triple point, which also is 6 millibars.
David, I thought all the CO2 ice that you get
Yeah.
doesn't equal the atmosphere.
Well, right, so the first thing I'm going to talk about is composition and chemistry, because those really are the fundamental things that set things like radiation. But what I decided to do was also have something of an anti-lecture on things we don't know. But I'm using that as a foil to explain things we do know. But essentially, as I look at it, scientific progress is about explaining the unfamiliar with the familiar. And so we need to identify the unfamiliar to see the useful problems to address in the future. I'd also say that knowing a subject's history is important. Old ideas, once dismissed, occasionally return to be the actual answer. Or, as we were discussing earlier, it's useful to know what people thought about when they were looking at solar system objects remotely in an exoplanet context. And although Isaac Asimov once said that the solar system is 4 planets plus debris, and I live on a piece of the debris, my focus is things that I've worked on, so it's Earth-like rocky worlds, mainly. And my interest in that is the same as members of the public, which is that those are most likely to harbor the sort of life we know. So this lecture has 4 parts. One is to talk about the classification, the different kinds of atmospheres out there, then structure of atmospheres, and in particular, talk a little bit about stratospheres, and then atmospheric chemistry in a nutshell, and a brief application to biosignatures. So why do we care about composition? Well, I care most because of habitability for the rocky worlds. And basically, the composition sets the radiation, sets the climate, sets the albedo. And what we're looking for is worlds that have liquid water on the surface, and you can be too cold or too hot. Composition is also determined, at least for the Earth, in large part by biology. Life dumps waste gases into the air. So here's a cow, and here's some grass producing oxygen and methane, respectively. And you can think of it, at least for the Earth, it really is an inorganic extension of the metabolisms in the biosphere. That's really a different issue, talking about the total mass. All I'm talking about is, given a surface temperature, you can predict what the vapor is. What happens is that the seasons, so the poles wax and wane. There's a permanent South Polar ice cap, but the average pressure is about 6 millibars, roughly. So the mass varies by about 30% because of seasons. So what we don't know, do these kind of things exist on exoplanets? And I would wager they probably do, because we've got more than one example in the solar system. It seems almost inevitable that there are some planets out there with surfaces of a particular volatile, and all you'd have to know is the temperature, and you'd be able to read off the pressure of whatever volatile it is. So what about trying to think about these different atmospheres and how to categorize them? You could group according to some dominant gas, Earth and Titan, Mars and Venus, but I don't like that. Bad student essay, 6 out of 10. Instead, a way I would prefer to think about it is more chemically based, and along this track that we know that certain compositions of atmosphere, like this one, will consist of hydrogenated gases, and hydrogen itself, and these are reducing. And then there are other compositions of gases. There might be minor reduced gases, but they're oxidized carbon or oxidized nitrogen, and these are more oxidizing, weakly reduced, because there's a little bit of reducing gas in there, but basically reducing and oxidizing. And that seems to me like a fundamental division. And so that we can talk about reducing atmospheres like Titan, the giant planets, the Earth, before it had a lot of oxygen in it, maybe Mars, sometime in the distant past, and oxidizing atmospheres, the Earth today, Venus. Venus is always the problem child of the solar system, but at altitude it's oxidizing anyway. If you get near the surface, it's a bit more reducing. And Mars, CO2. Why is this a useful way to think about atmospheres? Because it indicates the chemical character